the reservoir heterogeneity. We have discussed some of the general types of reservoir heterogeneity that are totally dependent on our scale of measurement. Okay, so today we'll talk about little bit the main types that we are mainly concerned in reservoir geology, and we will try to apply different kind of techniques to evaluate the reservoir heterogeneity. So whenever we talk about reservoir heterogeneity, so it means the deviation from the uh, homogeneous trend. Okay, are the properties changing with respect to space and time. If it's a heterogeneous reservoir, then there will be a change in properties as a function of spatial location. Spatial location means with respect to change in lat long or with respect to changing dimensions. There are properties like porosity, permeability, thickness, saturation, faults and fractures, rock facies and rock characteristics. They aren't homogeneous at everywhere in the reservoir. Uh, uh, with the change in direction, with the change of dimension, or with the change of spatial location, uh, uh, they pose a variability in their character. So we are interested either they are homogeneous or either they are heterogeneous. Okay. So basically, on a large scale, uh, there are two types of heterogeneity. One is vertical heterogeneity, and the second one is aerial heterogeneity. Vertical means with respect to depth, uh, what kind of changes are happening there, and aerial heterogeneity, lateral changes in any property. So we use different kind of geostatistical methods in the petroleum industry to describe these two types of reservoir heterogeneity. With the passage of time, the techniques of geostatistics has arisen exponentially. Uh, we are utilizing these statistical methods in reservoir modeling, in heterogeneity mapping, uh, as we have just consider the situation if you have uh, one well is in F8, it's nearby Barrier University. The second one is around Qaid-e-Azam University, and you are interested to know about the properties, the existence of properties between these two wells. So there is only one way out to know out some of the probability of existence of different properties between these two locations, that we can get the information by using geostatistical methods. Like we can use inverse distance method, we can draw polygon method, we can use different kind of statistics to just get an idea about the properties between the reservoir. Obviously, there will be a lot of uh, uncertainty in the values, but anyhow, up till 70 to 80%, if you have a cluster of data sets, I mean, if you have more number of wells drilled in an area and you want to know the probability of any property between those gray areas, then you can get up till you can get some information by using the geostatistical techniques. Okay. um, I hope you have an idea about geostatistical methods uh, while you were having the classes of GIS, because there are a few, there is an isolated section in GIS software that gives you an idea about the application of geostatistical methods. So let's talk about vertical heterogeneity first. So with the passage of time in a reservoir, when it goes up to development stages, uh, we get lot of data from different sections of the reservoir management. Like we get a lot of data from core analysis, we get a lot of data from well logs, and from different departments we need to integrate that data uh, to know the true dimension of the reservoir. So once you have the data, then you must have an idea how to describe the degree of vertical heterogeneity in mathematical terms. These are all mathematical terms and geostatistical terms you might be applying to describe the vertical heterogeneity. Uh, Describe and define the proper permeability stratification of the base zone. Uh, we are mostly interested in the zone of our interest, where uh, you have good less water saturation, hydrocarbon saturation, high porosity, and low gamma ray. So that is our pay zone. Uh, so if we have the data, and if we need to, if we are applying these geostatistical methods to know the heterogeneity with respect to depth, then this process is called layering or zoning problems. We create layers with the same properties. If the some properties are constant, we call that layer or that zone as a zone 1 or zone 2. If the zone has different properties, then we can divide that zone into subzones. Okay. So there are two widely used statistical parameters used to describe the degree of heterogeneity. One is Lorentz coefficient, and the second one is Dijkstra-Parsons coefficient. Okay, these two are important one. Most widely, they have been used in the oil industry to get an idea about heterogeneity. When I say oil industry, that doesn't mean every company is going to utilize these techniques to evaluate the reservoir in much more detail. Uh, uh, I guess if you go to some of the companies that I know, and if you talk about the heterogeneity or these coefficients or these statistical methods, they obviously look at you that it's something out of the context. Normally, it's not our practice to utilize these parameters to look into the reservoir with such depth. But anyhow, there are companies, research-oriented companies. They always come up with these parameters as well. So let's talk about Lorentz coefficient. Chamels and Ramey introduce a single parameter that describes the degree of heterogeneity within a pay zone section. So we call it a Lorentz coefficient. It's very easy if uh, and it varies between 0 and 1. 0 is for completely homogeneous system, and 1 is for a more heterogeneous system. So there are a few steps to get an idea about Lorentz coefficient. If you have normally we apply these type of tests in uh, for permeability, because permeability varies a lot as compared to rest of the properties. So if you have permeability data, the step one would be arrange all the available permeability values in a descending order. The second one is calculate the cumulative permeability capacity summation KH and cumulative volume capacity summation OH summation phi H. The third one is normalize both cumulative capacities such that each cumulative capacity ranges from 0 to 1. We need to bring the values between 1 and 100, mean 0 and 1. Okay. Plot the normalized cumulative permeability capacity versus the normalized cumulative volume capacity on a Cartesian scale. You need to plot all these values on a Cartesian scale. We'll perform one exercise so you will get an idea how to do it. This is the figure. If your values are on this line, this straight line, then it means this system is completely homogeneous. But if it deviates from this line, then there is a homogeneity in this your system or in the reservoir section you are particularly interested in. Then you can use one formula that area about the straight line, area below the straight line, to get an idea about Lorentz coefficient, or you can use this formula for area to get an idea about Lorentz coefficient. If it returns value 0, then it's completely homogeneous. If it gives you 1, it is completely heterogeneous. So let me show you. Let me finish first these slides, then we will come to one exercise. Okay. So there is a correlation of Lorentz coefficient and permeability variation as well. Like you can see from this figure as well. If we have high Lorentz coefficient, then there will be high variations in the permeability. Similarly, they are correlated with each other. So we have one equation that describes the Lorentz coefficient in terms of permeability variations, and similarly we have permeability variations in terms of Lorentz coefficient. The second most interesting coefficient is Dijkstra-Parsons coefficient. This is the dimensionless measurement of heterogeneity. It is a ratio of sample standard deviation to the mean. We use two standards. One is standard deviation, and the second one is mean of permeability. So it is Vk S over K bar. Okay. So it is also resides between 0 and 1. So we use one plot, one log probability graph for the computation of Dijkstra-Parsons coefficient. If you have permeability, okay, that is in Milli-Darcy, then if you have portion of total samples having higher permeability, you need to plot those values here. Okay, then draw a straight line just joining these points. Then you need to apply this formula. Vk is equal to K50 minus K84.1 divided by K50. K50 is here. Between 40 and 60 there is a it means it's 50%. You will draw a line just to join the to reach the point at the straight line. Then you will draw a horizontal line that is on sample permeability. So this is 10. Okay, the second one is 84.1. You will draw another line then this gives you around 2.5 permeability, and you will use this formula to get idea about Vk, that is Dijkstra-Pearson coefficient. You can also get this coefficient with the help of this formula if you are not using that plot, that is Vk is equal to 1 minus exponential of minus log Ka or Kh. They are the arithmetic harmonic average permeability. You must have these two permeabilities, arithmetic permeability and harmonic average permeability. We have already gone through this topic, that how we can get an arithmetic or harmonic average permeabilities. So once you have gone through all these steps, then if it returns the zero, then it's an ideal homogeneous reservoir. If its value is 0.25, it's a slightly heterogeneous. Similarly, if it gives you the 1, then it's a perfectly heterogeneous reservoir. Okay, so mostly you will get values between 0.25 to 0.75. Okay, so this is another example where we have 100, we have 0.75 as Dijkstra-Pearson coefficient. Okay, so it means it's extremely heterogeneous reservoir. Then we have another form, that is areal heterogeneity. So how we can get an idea about the heterogeneity or variations or variability once we are dealing with horizontal variations. So there are different parameters, or there are different techniques which we can use in order to capture the variability from one point to another. Okay, so basically we are predicting the values from from the unknown locations. So you might have gone through different contouring techniques. This is very much close to the contouring technique as well. We use polygon method, the inverse distance method, the inverse distance square method, the triangulation method, or Delaunay triangulation method to compute the areal heterogeneity. Polygon method, it uses different types of polygons. It draws a different polygons on a single data set, and then it measures the nearest values. Inverse distance method, um, uh, that the basic concept behind this technique is with inverse distance, data points are weighted during interpolation, so that the influence of one data set, it decreases or declines with the distance from the desired location. As the distance from one to another data set is increases, it gives you a inverse of the distance and gives you one unknown value at that point. Inverse distance square method, we just take square root of the inverse distance method to get the inverse distance square method. Triangulation method, it uses a triangle. Three samples must be there. If we have samples at three different locations, then it is going to give the value of fourth unknown location by using the triangulation method. Then Delaunay triangulation, uh, this is the formula to use the Delaunay triangulation method. Once we will be dealing with the software, you will get to know the by the utilization of these 3 or 4 methods, because normally we use these techniques in contouring, in geostatistical methods. If you have any idea or any experience working with the GIS software, then you might have gone through all of these polygon methods. One of the famous polygon method is Thesian polygon method. Okay.
Yes.
Okay, this was very simple and brief introduction of all these things. So we will go towards the actual application. से आवाज नहीं आ रही 005 now it's fine. आवाज आ रही है बाकी लोगों को?
Yes, sir.
Yes, sir.
Okay, I think you have issue with your own system. Is it visible an Excel sheet? Okay.
Yes,
So
sir.
I have point few values of permeability. Okay, these are the permeability values given to you, and this is the height of that section. Okay, so what we need to do is we will get all these parameters. First one is kh, like we need to multiply k and h. Okay, so we have got the kh. The second task is to get the summation kh. Okay, summation kh, we will let the first value like as it is, then we will use the formula this, then we will add this. Okay, so this is going to return us the summation kh. Okay, summation kh. So then we have summation kh divided by last value of summation kh, like is equal to this value divided by the last value 5671. So it is going to normalize the values between 1 and 0. As we have all the charts available, they are between 0 and 1. That's why we have normalized these values. Then we have another column in which we are supposed to calculate the summation h. Okay, summation h means let the first value as it is, then there is a first value plus second one. Okay, it is going to return you this one. Okay.
Yes.
Then we have another column in which we have summation H, the column we have in F, divided by the last value to make it normalized. Okay, so we will do it like this, divided by 56 was the last value. So this is going to return you this value. Okay, now
Yes.
uh, we are working on Lorentz coefficient first. Okay, so these two columns, we were provided with these two columns, permeability and height. We have calculated all these columns by ourselves. First one KH, summation KH, and then the last divided with this the last value, then summation H, then summation H was divided with the last value. Now we can make one a graph like insert graph. We will go to like this. We can just normalize this value between 1 and 0. Okay, then we will perform the same task. Okay, so we need to we need to change the x-axis and y-axis. How it's done? Like on x-axis, uh, there must be a values of summation S. Okay, on y-axis, okay. So you just need to ignore this one and utilize this curve. Okay, so what we have seen that our data is in like in arc shape. So if we draw one line from here, from the origin to here, that is about that describes the perfectly homogeneous system. But this is somewhat heterogeneous. Okay, are you getting my point?
Yes.
Like we have seen in one of the figure that if it obeys the straight line, if your values are in the straight line, then it's a perfectly homogeneous system. But if it's deviates from the straight line, then it's a heterogeneous system. Okay, so basically the data we have in this section, it gives you the heterogeneous system, and we can calculate the Lorentz coefficient out of this data as well. So similarly, we can calculate uh, the Dijkstra-Pearson coefficient from this data as well. So we will be using the Smithson H, okay, this data and the permeability data. And after that, we will use one chart to describe, to plot our data on that chart to get the uh, Dijkstra-Pearson coefficient. This is the chart that we use for Dijkstra-Pearson coefficient. Okay. So these are the simplest techniques you can use by yourself, and I'll send you the data as well uh, for your practice, so that you can apply these techniques on the real data set. I think it's enough
Yeah.
for today.
Yes, sir.
Okay, ji. See you